Welcome back, everyone. In the previous video, we introduced power series, which were the sort of culmination of all the things that we've been talking about with sequences and series leading up to now. Now, what we saw is that power series are sort of like infinite polynomials. They are just sums of every single potential power on some variable, say x. Now, what we saw in the previous video is how we can test for divergence using all of the notions and intuition and just results that we have from analyzing infinite series. Now, what I'd like to do in this video is some calculus, right? I want to talk about the properties of infinite series. What happens if I multiply two series together? Can I take an integral of them? Can I differentiate them? And the answer to these questions are yes. We can do these in sort of the natural way that you would think about. So that's what we're going to analyze as we go through the lecture today. And we'll sort of highlight this with some examples, and we'll use this to figure out what these series actually converge to sometimes in terms of the functions that we all know and love, maybe like the exponential functions or the trigonometric functions. So let's jump right in. And let's start by talking about multiplication of series. So these are all theorems that I'm going to lay out, but I'm just going to sort of write them, as the sort of what they do. So for example, I'm not going to write theorem here. I'm going to say multiplication of power series. Okay, so basically, we're going to assume that we have two power series. We ask ourselves what happens if we multiply them together. So let's say if capital A of x is a function given by a power series, let's say starting from 0 to infinity, an x to the n. So we're going to center these things at 0 just to make our lives simple. You can center them at any value and it'll still work. And let's imagine we have another one, b of x. In this case, starting from 0 to infinity of some sequence bn. And let's assume they converge absolutely for x in some radius, so less than some radius. Okay, so based on the results that we saw at the end of the lecture, we know that these things, they converge on intervals if they converge anywhere at all. So we're going to assume that there's some common interval where they both converge. And let's define, so Cn is equal to A0 Bn plus A1 Bn minus 1 plus A2 Bn minus 2, all the way up until we get to an minus 1 b1 plus an b0. The way that I was able to keep track of the terms in this sequence is because if you add up the indices, they add to n. 0 plus n, 1 plus n minus 1, 2 plus n minus 2, and so on. You can write this as its own finite series of a to the k, b to the n minus k. Then this new function that you create, n equal to 0 to infinity of Cn x to the n, converges absolutely. Absolutely to ax times bx on the absolute value of x less than r. And really what this says is that if you multiply these two power series together, you get another power series. So all that really matters is that they have the same values of x that they converge for, right? And they have to converge absolutely for this to make sense. We've seen places where you do not converge absolutely, things go very, very wrong, right? That was the conditional convergence regions. Now, in practice, this is not very fun, right? This is a very, very complicated formula that only gets worse as n gets larger for the coefficient Cn. So what do we do as mathematicians? Typically what we do is we just write out the first few terms here. So let me give you an example of how we write this. So we know that it converges, that's fine. We can use a computer algebra program to sort of parse this out for us. But let me show you what I mean. Let's take this sequence, our old favorite, just all of the powers of x added together. Let's multiply it by this sequence, so minus 1 to the n, x over n, x to the n plus 1 divided by n plus 1, okay? So what we typically do is we write out the first few terms of these things and multiply those together like they're a usual polynomial. So this would be 1 plus x squared plus, sorry, there's a lot more terms than just that, but I'm going to just tuck them into the dot, dot, dot. And the first few terms of this sequence are x, and then minus x squared over 2, and then plus x cubed over 3, and then blah, blah, blah. Okay, so I want to figure out what the series looks like, maybe up to the third or fourth power. Okay, so here's what I'm going to do. I'm going to take the 1 in the first sum and multiply it against every single element in the second sum. So this is going to give me x minus x squared over 2 plus x cubed over 3 minus blah, blah, blah. And I'll put underneath just by 1. That's multiplying the 1 into this thing. And then plus, let's multiply the x into this thing. So I get x squared minus x cubed over 2 plus x to the 4 over 3, blah, blah, blah. Again, we'll use a different color. We'll say by x, and that is the x going into this. I know it's getting messy, but I hope that the colors are helping you to parse this out. And then let's multiply the x squared in. I get x cubed minus x to the 4 over 2 plus x to the 5 over 3 minus blah, 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 blah. And let's put that one in red. That's by x squared. And that is my x squared going into this entire bracket. So this is a sum of infinite sums, right? So it's pretty ugly. But what matters is we can look at the lowest order terms, right? So there's only one x term anywhere here. So that is, let's do it in yellow. That's this one right here. Okay. Now where's all my x squareds? Well, I can see one right here, and I can see one right here, and that's it. So I have x squared minus x squared over 2. That is plus x squared over 2. Now, let's look for cubic terms. I've got an x cubed over 3. There's one. I've got a minus x cubed over 2, and I've got an x cubed on the back end. So I've got 3 of those terms now. And when I put all of those together, I get plus 5x cubed over 6. So this is not getting easy, right? And if you wanted to, you could keep going up to x to the 4. You could find that the next term is x to the 4 over 6, and then dot, dot, dot. But you can see that there's not much of a pattern, right? It's much harder in this case. And so, as I mentioned, mathematicians will typically just figure out what the first few terms are and kind of leave it at that. Okay, so multiplying power series, it works in theory. It's kind of a pain, right? It's a hard thing to do. It's not a trivial task. It's not an easy thing to do. So what we do is we typically leave it for the first few terms. All right, let me give you another result, sort of composition, right? So we're kind of redoing everything that we've done or that we know how to do for calculus. We know how to multiply continuous functions together. We know how to take compositions of continuous functions together. What happens if I take a composition of a continuous function in a power series? So now I have a theorem here. And let's say if the sum, so my power series, an x to the n, converges absolutely. Again, we always need that absolute convergence for this to make sense. For absolute value of x less than r. And f is a continuous function. Then the composition, so the series at f, so an, and then we have f of x to the n. Well, this thing will converge absolutely. on the set of points x such that the absolute value of f of x is less than r. So you have to be in the region where you can get convergence here for this to work. But how does this work, right? This is an abstract theorem. This can greatly simplify things. This can make our lives very nice. So for example, let's consider the following sequence. N is equal to 0 to infinity of, say, 4x squared to the power of n, which if you wanted to break this out, maybe I could give it to you. I could fool you a little bit. And I could say, actually, this should be the series of 4 to the n, x to the 2n. Okay, well, what we could do is we could say let f of x equal to, say, 4x squared, which implies that the series is equal to sum of n equal to 0 to infinity of f of x and then all to the power of n. But we know that this sum of all of the x's to the n's is 1 over 1 minus x, right? And so this tells me that my sum from n equals 0 to infinity of 4x squared to the n is equal to 1 over 1 minus f of x, which is equal to 1 over 1 minus 4x squared. And it converges for f of x less than 1, because we know that the radius of convergence for the series x to the power of n, the sum of x to the power of n's, that radius r is equal to 1. So this is the same as 4x squared is less than 1, which is the same as x squared is less than a quarter, which is the same as the absolute value of x is less than 1/2. So the new series that converges to 1 over 1 minus 4x squared, it will converge for all x between minus 1/2 and 1/2. The nice thing is that sort of compactifies a lot of our work, right? It allows us to look at more complex series that might not be sort of traditional power series, right? If you think of this series right here, you know, it doesn't quite, at least on the surface, look like it fits into exactly the form that we would want for power series. Now, if you sort of rearrange your indices, you can make it do that. But nonetheless, you can use this composition theorem in order to simplify a lot of the process. Okay, so let's think of something we love about polynomials. Right? What is it that everybody loves about polynomials? Well, they're easy, right? In terms of most functions, they are the easy ones to work with. And why are they easy? Because derivatives are easy and integrals are easy, right? And so if you think of what a power series does, is it's sort of turning functions into polynomials. And so what that means is that differentiating a function should be easier when we have the power series, because we can just differentiate all of the little polynomials that make it up. And that's exactly what happens. So let me give you another result that says that we can do exactly this. We can take derivatives of these power series just term-wise. So let's say if this sum Cn x minus a to the n has radius of convergence r greater than 0, so it converges for all absolute value of x minus a less than r, then it defines a function f of x is equal to this thing, right? So I'm just sort of restating our facts, but it's important for us to understand what this is really saying. On the interval a minus r is less than x, which is less than a plus r. This is the same as the absolute value of x minus a is less than r. I just opened it up for you. It's nice to see things a few different ways so that when we encounter them later, we're sort of familiar with it. So this function f has derivatives of all orders, of all orders inside the interval. And we obtain the derivatives, or the derivatives are given by well, in this case, f prime of x is equal to, so in our case, you're just differentiating term-wise. So you get n times cn times x minus a to the n minus 1, which I want to point something out to you. We don't need to start counting at 0 because now the first term is 0. That's being multiplied by n equal to 0. And this makes sense, right? The first term is constant. So under derivatives, that thing becomes 0. So I'm going to write n equal to 1 here. So I don't want to confuse you with this, but I want you to recognize why I can start counting at 1. And similarly, the second derivative is just taking the derivative of each element of this series. In this case, I'm going to get n and then times n minus 1. So I'm differentiating the first derivative, cn x minus a to the n minus 2, And in this case, I can start counting at 2 because the first term and the second term have been differentiated down to 0 under this differentiation. And you can keep doing this and so on. Each derivative converges. So each derivative converges at every point, at every x, such that x minus a is less than r. So you have the same region of convergence here. Now again, this is really nice, right? Because this allows us to do calculus, right? Most people think that calculus is sort of synonymous with derivatives, although I think that's incorrect. It's actually synonymous with limits. But nonetheless, this allows us to use sort of our traditional calculus knowledge, right? So we have a new way of talking about functions through power series. We have the same old manipulations for understanding them. So let's look at an example. Let f of x equal to the sum of, n equal to 0 to infinity of x to the n. So here we know f of x is equal to 1 over 1 minus x. So what this is going to allow us to do is find a series of other functions, right? Because 1, f prime of x is equal to, from our differentiation rule, we get n times x to the n minus 1. And we also know that this thing is equal to 1 over 1 minus x squared. So maybe if I draw some arrows here, that derivative here, and here is the other derivative. So now if you ask yourself, Jason, what is the derivative, what is the power series of 1 over 1 minus x squared? Well, it's n times x to the n minus 1. And this is on minus 1 is less than x, which is less than 1. Similarly, f double prime of x, this is the sum starting at 2 to infinity of n times n minus 1, x to the n minus 2, which we can again just take the derivatives here, and this will give me 2 over 1 minus x cubed. So again, the left side is coming from differentiating the power series. The right side is coming from differentiating the actual function that we already know. So again, what we can use this for is we can use it to find what the power series is for functions that we might be interested in. So maybe you wanted to know what the power series of 1 over 1 minus x all squared is. Well, you know that that thing is the derivative of 1 over 1 minus x. You know the power series of 1 over 1 minus x, and therefore you can find the power series of the function you're interested in. Okay, so I gave you differentiation. You know what's coming next, right? You definitely know that we're going to do integration next. And again, think about how nice integration is with polynomials. It is so nice, right? Integrating polynomials, it is almost as easy as differentiating them. Sometimes I get confused where the powers go, but nonetheless, it's fine. And so we have the same result. So let's suppose that we have a power series equal to a function. So let's go with n equal to 0 to infinity of Cn x minus a to the power of n, and it converges for x minus a less than r. And we obviously assume r is positive. So then this series, so then the integral or the antiderivative of f of x dx is equal to the sum, in our case, starting from n equal to 0 to infinity of Cn x minus a to the n plus 1 divided by n plus 1 plus c. And this converges for all x such that x minus a is less than r. So again, integration is awesome, right? Think about all of the annoyance, all of the trouble that integration has caused you so far through this course. Having to use things like trig substitution or partial fractions or some of these other techniques, even just integration by parts. What is this saying? It says that if you can find the power series representation of a function, integration is very, very easy, right? But the issue with this, of course, is that integration gives you another power series. And so you have to ask yourself, what does this thing converge to again? So you sort of still have the same issues, but you have an easier way of approaching the problem. Okay, so let's see how this works. Let me do this. Let's say identify the function f of x is equal to the infinite sum, so n equal to 0 to infinity of minus 1 to the n, x to the 2n plus 1 divided by 2n plus 1, which I'll just write the first few terms so you can get a handle on what's going on here. X to the 5 over 5 plus x to the, sorry, that's minus x to the 7, pardon me, over 7, and so on and so forth. And so with minus 1 is less than or equal to x, which is less than or equal to 1. So it's not immediately clear how we're going to be able to use integrals to help us here, right? This example is coming right after integration. So the question is, what can we do? Well, first, let's take a derivative. So let's differentiate. So first, differentiate term-wise. To find f prime of x is equal to 1 minus x squared plus x to the 4 minus x to the 6, and so on and so forth, where minus 1 is less than x, which is less than 1. Okay. This is just a geometric series, right? So this is geometric series. And it has the ratio equal to minus x squared. So this tells me that f prime of x is equal to the original first term, 1, divided by 1 minus x squared, which is equal to 1 over 1 plus x squared. Okay, so the derivative is equal to 1 over 1 plus x squared. Now, those who have probably been doing a lot of partial fractions or did a lot of partial fractions, this probably looks familiar to you, right? This should look familiar to you because this implies that f of x is equal to the antiderivative of f prime of x, which is the antiderivative of 1 over 1 plus x squared dx, which is equal to tan inverse, so the arctangent of x plus c. The question is, what is c? Well, the series, so above, if I put f of 0 or x of 0 into the series, so I get 0. And tan inverse of 0 is equal to 0. So f of x equal to tan inverse of x plus c implies that c is equal to 0. So therefore, f of x is equal to tan inverse of x. So we just had to take it one extra step in order to see that c was equal to 0, the constant of integration. But this was the nice piece, right? Because the derivative of this series is relatively easy, right? It's a geometric series. We can find exactly what this thing converges to. And so therefore, we can use the integration to get ourselves back up to the function just by using our integration techniques we've been developing. Now, I want to show you a really, really cool consequence of this. So for example, tan inverse of 1 is equal to pi over 4, right? That's when sine and cosine are equal to each other. And then now we have an infinite sum representation of what pi over 4 is, because it's minus 1 to the n over 2n plus 1. How did I get that? I put x equal to 1 just into that series that I determined is equal to tan inverse. So the series that we started with is in this example, now we have a representation for pi over 4 as an infinite series. And this is how we can find sums of infinite series. Okay, let me show you another example. So maybe this one will get you excited. So let's say, let's note that 1 over 1 plus t, this thing is equal to the infinite series 1 minus t plus t squared minus t cubed plus t to the 4 minus blah, 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 blah. All right, so I just wrote out the first few terms of this power series. This converges on minus 1 less than t less than 1. So I threw you a bit of a curveball. I changed the independent variable from x to t. That's okay, right? Nothing too exciting has happened. But what is exciting is I know that if I integrate this thing, I get the logarithm. So in particular, I get the logarithm of 1 plus x is equal to the definite integral from 1 to x of 1 over 1 plus t dt, which is equal to t, so we do term-wise integration, minus t squared over 2 plus t cubed over 3 minus t to the 4 over 4, and so on and so forth, going from 0 to x, which tells me that the series for logarithm of 1 plus x is equal to evaluating x at this infinite series, x minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4, and so on and so forth, which you can write compactly as the infinite sum from n equal 1 to infinity of minus 1 to the n minus 1, x to the n divided by n for these values right here. So that's kind of weird, right? We have a nice series representation of ln of 1 plus x. And maybe you're kind of just saying, okay, who cares, right? Well, what was the point of doing that? Well, I want to tie this back to something that I've been talking about a lot, right? Let's look at, so in particular, at x equal to 1, we have, okay, so we have ln of 2 on the left-hand side, ln of 1 plus 1. And on the right-hand side, I've got n equal 1 to infinity of minus 1 to the n minus 1 divided by n, which is what? 1 minus a half plus a third minus a quarter plus a fifth, and so on and so forth, which is what? It's the alternating harmonic series. So remember, I have kept saying in the past few videos that the alternating harmonic series converges to ln of 2, and you probably didn't believe me. Well, here I have shown you exactly what the alternating harmonic series converges to. And this is one of the great powers that these power series are going to have for us. We can use them to figure out what infinite sums actually converge to, because we can figure out the explicit function that these things are converging to, such as ln of 1 plus x. And then we can start plugging in values in order to see what these infinite series actually converge to. This was a major shortcoming of a lot of what we talked about with the series videos, because I just kept saying you can check if they can converge, but we don't know what they converge to. Now with the power of power series, we can not only determine, or we not only have new representations of functions through these infinite sums, but we can use those representations to figure out what infinite series actually sum to.